Gears have many applications in our modern society. We use them for cars, clocks, bikes, toys, pretty much anything mechanical. The cogs or teeth on gears are what make the magic happen. They interlock, allowing for the transfer of power from one gear to another, and when two gears have different amounts of teeth, you create a gear ratio between them. Gear ratios are what allow you to have a mechanical advantage, making something seem lighter because you've increased the amount of torque that you're able to generate by using a smaller gear, like so. You could also use the gears to speed something up, like so, allowing for neat tricks like this when you've got multiple shafts spinning at all different speeds, despite being driven by the same gear. So what can we do with this information? Well, a lot. We could make gearboxes that power drones, cars, planes even, but I have something much more important planned for today's video. We're going to make fidget spinners. Well, not that kind of fidget spinner. We're going to make gear spinners that interlock and drive each other. I'm going to use spur gears for this design because they're the most efficient type of gear, capable of efficiency up to 99%. This means that when you're using a spur gear to power another spur gear, up to 99% of the energy that you put in will come out. The other 1% is lost to frictional forces between gears and the air. So, in making a spur gear, you'll notice I have a few numbers to plug in. Starting with the pressure angle, it's the angle between the line of action and the line tangent to the pitch circle. We'll keep ours at 20 degrees. The larger angle distributes the force more evenly along the tooth profile, which reduces the likelihood of tooth failure or deformation under heavy loads, under normal circumstances. But it won't matter anyways, since none of these gears will be under any significant stress. Next is the module, which is the measure of the gear size and determines the size of the teeth. It's the ratio of the gear's pitch diameter to the number of teeth. In metric units, the module is expressed in millimeters, and here we have set it to 12.7. Backlash is the small amount of play or clearance between meshing teeth. It prevents gears from jamming and compensates for manufacturing tolerances, in our case 3D printing tolerances, which are up to 0.1 millimeters, so we will set it to 0.1 millimeters. Finally, the pitch diameter is the diameter of the pitch circle, which is an imaginary circle that rolls without slipping with the pitch circle of the mating gear, or the meshing gear. It's a critical dimension because it helps determine how the gears will mesh. While I'm making the last few finishing touches on this gear, let's talk about why spur gears are so efficient. They have a constant mesh. The teeth of spur gears mesh smoothly and continuously because they engage one at a time. This ensures a consistent transfer of motion and torque, leading to efficient power transmission with minimal losses. They are formed with an involute curve profile, which means teeth rub against each other like two circles rubbing, which only contact one another at one point, which results in minimal rubbing and minimal power loss to friction. Okay, looks like our gear is done. All that's left to do is put bearings in the center of these gears to allow for smooth spinning. There's more on how these bearings were designed in another video. On to the assembly. These parts were printed with the Creality K1 and are also available on Thingiverse for your enjoyment. I've also designed and printed one other gear size so that we can see our gear ratio of 1 to 2 in person. Now that everything's been printed, let's try out our first fidget spinner. You'll notice it's a bit loud, and that's because of all the balls in the bearing rattling around as it spins. Now, let's try powering another 24-tooth gear with this one. Notice how while they spin, when the first gear makes one revolution, the driven gear also makes one revolution, and this is because the gear ratio is 24 to 24 based on the teeth, or 1 to 1 simplified. Moving on to our smaller gear, you can see since it only has 12 teeth, it's about half the size of our 24-tooth gear. Once again, if I power a 12-tooth gear with another 12-tooth gear, we get a 12 to 12 or 1 to 1 ratio, so as our first gear rotates once, the second gear will also rotate once. On to the fun part, one 24-tooth gear powering one 12-tooth gear. You can see that as the bigger gear rotates once, the smaller gear rotates twice, which means the smaller gear is spinning faster in terms of angular velocity, since we've created a 2 to 1 gear ratio coming from 24 to 12 teeth. Now, if we power the 24-tooth gear with the 12-tooth gear, we get the opposite, a 1 to 2 gear ratio, where when the smaller gear rotates once, the bigger gear only makes half a revolution. We may have slowed down our output gear, but we have generated twice the torque that we put in. Well, that's it for this video. I hope you enjoyed it and learned something in the process. Stay curious.